All righty, welcome back. We're going to open up with a few clicker questions off the top, as usual, for the start of the week. And we'll start off with our linear transformation questions. The main new topic from last week that we're going to explore it further this week. Lights, okay. There's a question missing. What the hell? Sorry, there's no question. There we go. Let's try that one. Sorry. Sorry, I proofread that before I came. It's a little rocky off the get-go. That's fair. It's only one of those things, not all four of them at once. So let's talk about this for a second. Good. I'm glad I asked. All right. So the image. The sense of it is like something projected. At least if you think of, that's how I think of the word, like image projector going onto a screen. So it's where things go. So if I had to draw a mental picture for this, it would be our usual two sets. Here we're calling V and W. And the image are the points that can get reached by the transform. So all these points on the right-hand side are the points in the image. So this set here is the image of L. Points in the output that can be reached. That can be reached by L. Or, to be more specific or more technical about that, the image of L is a set, and it's a set of elements, little w, that are in big W, such that there exists some little v in the input, some input v, such that L of v equals W. That's how. That's the way we'd capture can be reached, is there's something in the input somewhere over here. If I pick a point, it's in the image because it has a precursor, something that maps to it from the input space. All right. And one of the things that we proved last week was that it wasn't just a subset. I mean, it is, but that's not the most interesting thing. It's actually a vector subspace. So if we're talking about our usual R dimensions, R2, R3, R4, this will be a plane or a line or something of that ilk. It won't be just some random set. It'll actually have all that structure closed under addition, closed under scalar multiplication. All right. Pause there for a moment. Questions, comments? Both the kernel and the image are vector subspaces of their respective inputs or output spaces, exactly. All right. Show hands is ringing some bells now. It's just been a few days, and that's all. A little rough. Okay. All right. So, kind of a quick follow-up to that. If we had those two sets from V to W, two sets, V and W rather, L. What can we say about the image of L? Fantastic. Give another 5 or so seconds. Again, click in, sticks to your brain better. All right. not too shabby. All right, we're looking strongly at B, and that is correct. Again, just kind of like that diagram on the last page. It can be some of W, it can be all of W. We don't know. It depends on the individual function and the input and output spaces, but it's going to be something about the output space. There was something here that we talked about last week with kernels and zeros and stuff like that, but it was something a little bit different. We said there's an equivalency between the kernel of L being just the zero vector, and that was the same thing as saying that only the zero vector input maps to the zero vector output, because all linear transforms map 0 to 0 no matter what. That's one of the results of being a linear function. But sometimes other points might also map to 0. But if we had this, that turned out to be equivalent to, or if and only if, some other statement about the function. Bit of a deeper dive here. Do you remember what that other property of the function would be of that L? Yeah? L would be injective, exactly. L is injective, or one-to-one is the other way we phrase that a little more colloquially. So there was something about kernels and zeros and stuff, but it was about the function mapping just one point to one point. It turns out if that's true for 0, if the function is linear, that means it's true for all the other points. They only map one input to one output. Or the outputs are unique, otherwise say it. All right, I think that's about it for that. Yeah, so what we're going to do is take a quick pause for a second because life got sort of exciting. We had 2 unions that were potentially on strike as of today. One of them settled, one of them didn't. So I'm just looking at the consequences for all your different courses. They're going to be a little bit different depending on how that all worked out. So for 174, the PSAC TA strike, the main effect right now is that section 103 to 105 has no instructor now, which is a bit of a problem. Because they were a graduate student. They are a graduate student. So they're going to be invited to come to our classes or watch the online recordings from the lecture capture, that kind of thing. I think that's the only, we seem to have room, is what I'm saying. There's some empty seats around. But I think that's the only effect in this course because your tutorials are all run by Apple Math undergrad students, so they're part of a different group. And so tutorials run as normal. And you would have seen that for 172 as well. Your tutorials today and tomorrow, depending when you have them, are going to run as usual as well. The complication for calculus, because we're all in the same boat here, calculus is that you have a test on Thursday and the graduate TAs were proctoring it. They're on strike, so we're not sure how that's going to play out. So we're in discussions today to get some results or some answers for you, hopefully by the time we have our calculus class this afternoon, about what's happening on Thursday evening. So a little bit up in the air, and I apologize for that. That's where we are. Questions or other things haven't mentioned there? Please. Exactly. So if you look at your like chemistry, everybody that does chemistry is either a prof or an undergrad TA, as I understand it. So everything in chemistry is running as normal. Every course has a different mix of graduate versus undergraduate. It's strictly the graduate TAs that are on strike at the moment. And for totally valid reasons, I will. Yeah. I saw a thing the other week about someone applying for a grant, and they said, oh yeah, and by the way, the regular stipend for graduate students right now is $17,000 a year. I'm like, okay, that's starvation wages to start with, and then you pay tuition out of that. I'm like, what? How do you, yeah, exactly. I'm like, and you eat what? Like seawater for a year? Anyway, it's insane. So, but it's also complicated because the graduate work that TAs do is one pile of money. It's like, okay, if they get paid a reasonable amount. It's like $40 an hour, but they only get to work 10 hours a week, and meanwhile they get some support for their research. It's a whole mess. It's under different guidelines. Some of it's federal, some of it's the university. Yeah, so it's super complicated and not easy to work out. It does not totally shock me that that's the one union that didn't come to an agreement, because their situation is just way more complicated than work conditions and pay run by the university. I have no idea what state they're at. I have no inside knowledge on that, so I have no idea if this is going to be like a 4-month thing or a 2-day thing. No idea at all. So we're going to have to play it by ear. As I say, the main thing is tutorials will run in this course and in 174, and chemistry. All the other courses, you should get updates from your individual instructors. Anything else? Strike-wise affected? Fantastic. All righty, then. Let's keep doing linear algebra, all right? Going from the concrete to the abstract. All right, so for a linear transform, we have two major sets. Two major sets. We have the kernel, and we have the image. So we're going to return to these two sets over and over, so just to remind you about what they are. We saw the image a second ago. Let's do it first, because we just did it. The image of L is equal to the set of all W's, such that, now we'll use the fancy there exists symbol, that backwards E, because we've introduced the concept. There exists a V in the input such that L of V equals W. Okay, so if we have a W here, there's a matching V input that goes to W. On the kernel side, this is all about the zero vectors on the output. So the kernel of L is a set of all input vectors. So let's say the V, V, such that L of V is equal to the zero vector. And draw little pictures here. So V and W. So if we have the zero vector here on the right-hand side, there will be some set of points that all map to 0. Again, it's a vector subspace, so it could be a line, it could be a plane, or it could just be a point. It could just be the 0 dot, and that's all. But there are going to be at least one point, possibly a subspace, a larger subspace, that maps the 0 vector on the outside. And so we're interested in that space, and we're interested in the image, which is all the points that we can reach with on the output side from our transformation. All right. Now, when we look at linear transforms, there are now several different forms we've built up or used along the way. So this would be sort of the calculus, right? If we had a function, here it is. Here's the brackets, commas, all that jazz, components. In linear algebra, we have other options for representing that. And so if we break it down by x here, then I'd have 2 x's, and then I'd have 1 x, and then I'd have 4 x's. And then I'd have negative 3 y's, and a 1 y, and a 5. And that would be an entirely equivalent way of writing that function, right? If I expand that out component by component, I'm going to get 2x minus 3y this way, or I can get 2x minus 3y that way. It's the same thing. Then we talked last week about the standard matrix form. So standard matrix form. And that standard matrix captured in one column the transform of the 1, 0 vector. So this column here is what we get when we transform 1, 0. Well, wait a minute. That's really easy to get once we have the form before it, because if I transform 1 and 0, well, the 0 part just goes away, and I get 1 times this vector here. I just get 2, 1, 4. And then if I transform the other fundamental basis vector, 0, 1, well, x is going to be 0, so ignore all that. And I just get 1 times this thing, so we get negative 3, 1, 5. There's no transformation, there's no scale. We copy the numbers down into a matrix form. And then another way we had to write this all out was just to take that matrix and write it, if I think of it as a transform of x and y, we did this sort of dot product-y thing at the end of last week. We'll do some more of that again this week to reinforce it, but there's a way to interpret this matrix times xy that gave us the form up here, which is the same as the form at the top. So these are all the same thing. They all represent the same transform. And that means we can give any one of these forms to you. We might say, here's the matrix for your transform. Fine. Here's the function. You should be able to switch between the various forms. Unfortunately, it's pretty straightforward. It's like, what are the coefficients of x and y? And then literally just list off the coefficients of x and y in a matrix form. That's it. Yeah, please.
So the standard matrix always shows the fundamental basis vectors. So it'd be so like 1, 0, or 0, 1, or like I and j.
Yes. So this matrix will show only the transform of those archetypal basis vectors. We're going to show an example where, what if we had other vectors? That'll be our next example. And what matrix, yeah, let's get to exactly that. I think it's a nice segue for it. Hey, what if we don't know the transform of those simple basis vectors? What if someone tells us instead that we can transform 3, 2, and this is a mapping from R2 to R3. So we have R2, and we're going to go to R3. We know just that the vector 3, 2 maps to, through our function here, L, it maps the point 9, 1, 5. There it is, 9, 1, 5. That's 3, 2. And we also know that the vector 4, negative 1, maps to some crazy, over here somewhere. Maps to 12, negative 6, 3. And we're asked to find either basically the definition of that transform, specifically in standard form, the standard matrix for it, which is essentially finding what's the function? How can I write out the coefficients of x and y as we know and love the basic building blocks? And here we have a whole cascade of lovely ideas that come from linear algebra that let us do this. So 3, 2 and 4, 1 are vectors. Are they linearly independent of each other? Yes, they're not multiples, 2 vectors. If they're not multiples, they're linear independent. Nice and easy for 2 vectors. There's 2 of them in a 2-dimensional space. What's another name I could give to the set of 2 vectors? They're linearly dependent? They're basis, right. I can reach anywhere in all of R2 with linear combinations of the green vector and the red vector. Specifically, I can get to the vector 1, 0. I know that if I add some multiple of 3, 2, probably a small one, and then some multiple of 4, negative 1, I'll be able to get to the vector that I actually care about for this problem, which is the vector 1, 0. So let's make a quick note of that. We have the vector 3, 2 and the vector 4, 3. Those together are a basis for the input space R2. And that means that 1, 0 and 0, 1. 0, 1, the 2 elements we need for the standard matrix. Are in the span of 3, 2, 4, negative 1. Damn it. All right. So I can build a linear combination of them. I can build a linear combination of 3, 2, negative 4, negative 1, and get 1, 0 if I like. I can also do it again and get a linear combination that gives me 0, 1. And that is going to turn out to be all we need, because when we take the transform of those things, we know that this function is linear, so we'll be able to break down this transform and re-represent it in terms of the vectors that we actually want. Let's do this actually play out here. So let's do a little line here. So what we're going to do is we're going to solve for how do I get 1, 0 out of some multiple of 3, 2, and let's keep the same order we had before. 3, 2a plus 4, negative 1b. And we're also going to want to do the same thing over here, but we're going to build the 0, 1 vector. And we'll use different coefficients for this, c and d. right. So we get, oh wait, shockingly, solving systems of linear equations appearing is a key step in our process here. So what do we get? If we look at the components, we could do this in matrix form, but it's just 2 by 2, so let's just jump to it. Components, we have 1 equals 3a plus 4b, 0 equals 2a minus b. That equation and the second one here pretty much gives us b. b is equal to 2a. We'll sub that into 1, and we get 1 equals 3a plus 4 times 2a, 11a, a is equal to 1 over 11th, and b is equal to 2a, which is 2 over 11th. And, whoops, sorry. And that tells us that 1, 0 is 1/11th times the 3, 2 vector, and plus 2/11ths times the 4, negative 1 vector. Let me double check. 3 plus 8 is 11, perfect. And 22 minus 22, yeah, perfect. Yeah, good. All right, follow up. We do the same thing on the right-hand side. So we're going to look at components over here. We're going to get 0 equals 3c plus 4d's, 1 equals 2c minus d. Kind of a toss-up which way to go. Let's call it 3 and 4. Let's go d equals 1 minus 2c. All right. 2c minus 1. Plug that into equation 3, and we get ourselves 0 equals 3c plus 4 times 2c minus 1. 4 equals 11c, c equals 4 over 11, and then d is equal to 2c minus 1. That's 4/11 minus 1, that's 8. I think it's minus 3/11. Turning the crank, doing the calculations, and we're going to be able to check that as well. What we should see is that 0, 1 is equal to c 4/11 times 3, 2, minus 3/11 times 4, negative 1. Check that. We get 12/11 minus 12/11 is 0. We get 4 plus 8 plus is 1. Perfect. All right. Any questions about the process there? Please.
The entire time here, we're only working in the input space.
Yes, we are only working in the input space because of our standard matrix definition that we want to transform 1, 0 from the input space and 0, 1 from the input space. Yes. Now we're going to take the leap to the output space. So we know the 3, 2 transforms to 9, 1, 5. Great. We know that 4, negative 1 transforms to 12 minus 6, 3. Fine. Because the function is linear, though, that means I can write my 1, 0 vector like we just did. Here we go. 1, 0 is equal to this combination. But then when I transform 1, 0, it's the same as transforming this, because they're the same vector. And then we can use linearity to break this into pieces. So that's what we're going to do here. We need the L of 1, 0. But that's equal to the transform of 1/11. Let me make sure I get the coefficients right here. 1/11 to 11th, yeah. 1/11 times 3, 2 plus 2/11 of 4, negative 1. Because this and this are equal. They're the same vector. But through the magic of linearity, what can we do with this thing? Yeah.
You could like split it up and move the outside.
Exactly. We can split it up. We can move the coefficients outside. We can write all of this as transforms of individual vectors, but specifically the vectors that we know the transform of 4, negative 1. And we know both of those. And so we get our combination 1/11 times their transform, 915, plus 2/11, 12 minus 6, 3. And we do some math. 9 plus 24 is 33. 33, 1 minus 11, 5 plus 6 is 11. Oh, that's nice. It's just 3 minus 1, 1. And that will be the first column of the standard matrix, of our standard matrix for L. That's the first column. For L. We're trying to build that standard matrix form, which is the transform of the sort of iconic basis vectors 1, 0, 0, 1, et cetera. We now have the transform of 1, 0 is this. We're good to go. Follow up is the obvious. Okay, I need the transform of that other vector, that 0, 1 vector as well. And we'll do that on the next page. So let me just pause there for anyone still copying. We got everybody? All right. Then let's go to the next page. Oops. Apparently I didn't leave enough room. So we also need the transform of the 0, 1 vector. But we found that it had a nice decomposition as well, which was 3/11 times 3, 2, plus negative 4/11. Is that right? No, sorry, negative 3/11 plus 4/11 times 4, negative 1, because that vector is equal to that vector there. And then we could use linearity to break that into what we expect, or what we did last time, plus 4/11, square bracket, square bracket. And then we know these transforms again. And what did I say, 915? 915, 12. And 12, negative 6, 3. And if we do that, we get ourselves negative 27 plus 36. Oh, I'm going to use my crutch. Plus 36. Nope. I thought they worked out nicer than this. I'll keep going. Sorry, I'm getting a weird number here. That's unexpected. Oh, it's 48. That's because I can't do math. Minus 27 times 48. There we go. Minus 27 plus 48. That's the, no, that's not right either. Damn it.
3 over 11 and 4 over 11 in the wrong.
Thank you. Going back a step here. Thank you. Yes, 411 comes first and negative 311 comes second. I tried to craft it so it worked out nicely. This is a good check. So my apologies for that. This should be 4/11 and then negative 3/11. 4, negative 3. Right, we solve for it in the opposite order. That's better. 36 minus 36, yeah. So we get a 0, and then we get 4 plus 18 is 22. That'll be 2. And then we get 20 minus 9 is 11. That'll be 1. Thank you for letting me know about that. That's what I was hoping for. And that is the second column of our standard matrix, because it's the transform of the 0, 1. And that means that A sub L, the standard matrix, for L is equal to 3, negative 1, 1, 0, 2, 1. All right. Thoughts, comments, questions?
From this, we can define the actual function of L.
Yes. So if the question was then, okay, you found the standard matrix, can you write L out like you would in calculus class? You can absolutely do that. L of xy would equal 3x plus 0y, negative x plus 2y, and x plus y. So we could, once we have that standard matrix form, we can interpret in a way that we couldn't just from those building block transformations, the 3, 2, and the 4, negative 1 transforms. What I think the deeper message here is, though, this standard form is straightforward to get based on relatively little information. If we go back to what we actually got told in this problem, we got told that out of the whole entire universe of possible vectors, this vector maps to that one, this vector maps to that one. That's all we need to fully define any linear transformation, so long as those two vectors were a basis for the input space. So because I had two vectors in 2D that were linearly independent, check, check, we have a basis, and so that means we can automatically get the transform of 1, 0, and 0, 1, or if we had more dimensions, we could get the construction of all those basis vectors. And as soon as we have that, we know everything we need to know about our function. So we don't need a lot of information to define a linear transform. Just a few building block transformations, and that's all we need. Everything else we can figure out, courtesy of all the theory we've been building up along this semester. Alrighty. But this also makes a nice midterm question. You'll see old midterms that have this kind of thing, like, hey, do you know what the standard matrix is? It's the transform of 1, 0, 0, 1. Okay, so what does this information help you get? Well, it helps you represent 1, 0, and 0, 1 in terms of the vectors you have information about, build that up, and away you go. Alrighty. Let's get to, oh yeah, this is sort of a deeper level theory that we're going to sneak up on here. So back to the kernel and image. Kernel and image are subspaces. The kernel is a subspace of the input space. Remembering all the things that map to 0. All these things map to 0. That's the kernel. And then the image is a subspace of the output space. It's the points we can reach. Space. There we go. All the points that we can reach from some input on the left-hand side using L. All right. Now, because they're subspaces, we have this other nice corollary that they have bases and they have, as a result, dimensions. Right? If we have a subspace, it can be spanned by a certain number of vectors that are linearly independent. Well, that'll be a basis. The dimension is the number of elements in any one of those bases. So what we can do then is extend that idea. So we thought about linear transforms. We can also talk about the kernel and image then of a matrix too. So if I just go back here for a second, this matrix somehow is the transform. And so if I put that lens on, someone just hands me this matrix and goes, here's a matrix. If you think of it like a transform, that transform will have a kernel, it will have an image. So we also use the same, we'll often say not the kernel of this transform, but the kernel of this matrix, and the kernel and image of this matrix. That's pretty standard. Let's see how that plays out here. So let's take a linear transform, in general from nice vector spaces Rn to Rm. We can guarantee one thing about the image. So the image is about the output, and if we take a look at the columns of A, they're going to be a generating set or a spanning set. Those are the two equivalent phrases for the image of L. And you can see why here. 2, 1, 4, 3, 1, 5. The image of L is equal to all of the ABCs such that L of xy is equal to ABC. in this case here. So in this scenario here, what's the image? The image is all output vectors, and we're going to, in this case here, R3, such that when I plug in some xy, I get to that point. But if we take a look at this, we can actually expand this out. This is equal to, from right up here, this version, it's equal to 214 x plus negative 315 y. And that literally tells us what a spanning set is. What building block vectors will cover all of that set? Well, the two vectors I'm building out of that. I can pick any x and any y, and I'm going to multiply them by these two vectors here. That means that the set 214, negative 315 here, is a spanning set for the image. We have lots of words going around here. Spanning set for the image of L. And again, that's just because what is the image of L? It's all the linear combinations of those two vectors, so they're going to be a spanning set. I can make everything in the image from those two vectors because that's how we're making our image anyway. All right, so that's generating set. Fantastic. But we want to get to dimension. We get to dimension through basis. Is it enough for a generating set to be a basis? No, we need one other condition for basis. It has to be I heard something weird, but I also heard linearly independent. Perfect. So no, we also need linearly independent. Sorry, let me be more simple here. The set to be. Okay. But it's a nice start. If we have generating sets, we can get to we can reduce it down if we need to get to a linearly independent set. It's a good building block. So let's take a look here and a couple scenarios. Again, remembering how the dimensions work here, this one would be a function from R2. We know it's that because there are two columns, and each column is L of 1, 0, L of 0, 1, and dot, dot, dot if we had them. Over here we have the same structure. This is R3 though, because we have three columns. And they're the L of 1, 0, 0, L of 0, 1, 0, and L of 0, 0, 1. So we can read off the input space by counting the number of columns. And then the number of rows is equal to the output dimension. So this is going to R3, and this is going to R3 as well. And we know that because we just said in the last thing, the image is built out of these column vectors. Well, they're three-dimensional, so my image is in 3D. I have these three-dimensional vectors that I'm using to build my image. All right, so we have here a consequence from the last slide, that 2, 1, 4, negative 3, 1, 5 is a spanning set for the image of L. We just grab all the columns. That'll always be a spanning set, a generating set for the image. Then we want to check that second criteria. Is it linearly independent? So this set of two vectors, is it linearly independent? Yes or no altogether? Yes. Yes, absolutely. Two vectors, not multiples. Two vectors, not multiples. That means that they're also linearly independent. Linearly independent. And that implies that this set is a basis. Set is a basis for what? For the image of A. For the image of A. And that means that the image of A is two-dimensional. even though it's in 3D, the actual point that we can reach, which is the image, is only two-dimensional. And if you think about that for a second, you can actually draw this out. Here are two vectors hanging out in 3D. I can take, what the hell 3D was that? Let's try that again. There we go. We have two vectors, our 2, 1, 4, and our other vector over here, negative 3, 1, 5. Hey, what construction can I build out of those two vectors if I'm allowed to use any linear combination? Well, I get a plane. Two building block vectors, you get a plane. If they're linearly independent. Compare and contrast with the example on the right here, though. This set here, I'm just going to erase this. We don't really need that for the moment. Delete. If we have those three vectors, they are still a spanning set, 2, 1, 4, 4, 2, 8, and negative 3, 1, 5 is a spanning set for the image of B. Spanning set for the image of B. All the points in B are reached by some linear combination of those vectors. Are they linearly independent, though? No. Yeah, this one, little softball. It's often harder to check with three vectors, but here, hey, those first two look pretty similar. In fact, they're multiples of each other. So it's not linearly independent, though. However, we can always fix that. If we remove, and we have a bit of a choice here, but let's remove the second vector here. If I take this vector out, so remove specifically 4, 2, 8, 4, 2, 8, then we get the set 2, 1, 4 and negative 3, 1, 5 is linearly independent and therefore a basis. I didn't talk about the spanning. I'll talk about that. I'm running out of room, so I'll just talk about it rather than writing about it. So these three vectors are great. They can reach everywhere. But because there's a linear dependence, I can take some of them out. One is a linear combination of the others. In fact, we can see this one's a linear combination of this one. So I can cross this off the list and still span the same reach. Remember, if we take one element out of a linearly dependent set and it's a combination of the others, well, it's not adding anything to the reach, to the span of that set. So I can take it out, and once I get to that point, I get two vectors that are linearly independent and still span that whole space. And so what we have in this case here is the image of B, even though it came with a 3 by 3 matrix here, is two-dimensional as well. A basis for it has only two vectors in it, so it feels like a plane in 3D here as well. And you can kind of see it's like we had two vectors in the same direction in this example. I don't get anywhere extra with that extra vector, so I'm still covering the same space, and we can capture that idea with the numbers of elements, numbers of vectors that show up in a basis. All right, sort of a mix of theory, sketches, and everything else. There is no difference between the image of a matrix and the image of a function. As soon as someone says, here's this matrix, what's its image, we're immediately going, oh, I'm going to pretend it's the standard matrix for a transform. So, and that's the language that we use. Because, yeah, we're going to see it shortly that we use matrices as multipliers, and then they are being used as a transform. That's the most common use for them. Yes, the image of a transform and the image of its matrix are the same. Exactly. All righty. Now that was a lot of thinking on the last page. I'm a big fan of finding ways to not have to think so hard, and we're going to discover one approach here with that. Here's the original matrix for A, and here is its RREF, row reduced echelon form, reduced row echelon form. Here's the matrix B, and its reduced form. All right. If you just take a look at these, let's look at vectors again, because we're talking about the linear independence of vectors. Are these two vectors here in the RREF linearly independent, yes or no? Yes, absolutely. These two things here are linearly independent. So it seems like, too many L's. Well, sorry, it doesn't seem like. Here's one data point to generalize from. In this particular example, it feels like, hey, he's looking at RREF for a reason. We know these are linearly independent because they have different components in them, right? This has an X component, this has a Y component. We can't make an X out of a Y. They're going to be linearly independent. And apparently that's going to tell us something about the original matrix back here. Same thing is true here. If I take a look at these two columns here, they are also linearly independent. And this column here is redundant, or for span, redundant, or it's a multiple combination of the others, of the other columns. And so it doesn't really play a role if I'm talking about span, if I'm talking about basis. I don't need this vector here, and it's very obvious in this scenario here that this vector is somehow different than the columns with leading ones in them. So we're going back to this leading one idea. So again, this is very much, hey, look for a pattern and see if it kind of makes sense. If we look at the columns that ended up with leading ones, in this form, they're definitely linearly independent. This column here and this column here, one's going in the X direction, one's going in the Y direction. Those are linearly independent. They can't be made out of each other. This one in the middle, yeah, it's redundant. It is literally 2 times the first vector, and so it's the thing that makes a set linearly dependent, but I can cross it off and reduce it to 2 vectors that are a nice set, a nice linearly independent set that still spans the original space. And that's going to be the pattern, that's going to be the strategy we're going to use to track down a basis. And we will do that tomorrow, or Wednesday. Yeah, perfect. Thank you very much. We'll see you this afternoon for calculus.